So here I just remind the introduction of the axiomatic of probability by Kolmogorov, which states that in fact probability is just additive set theory with the important peculiarity that there is the independence that make the peculiar stamp of probability theory. So basically consider that information is very independence is very important. I even consider that for real science, for natural science, the very important question is to see if two events are independent or not. So basically, yeah. So links and nodes. What are links? Links are in fact a collection of nodes that are non-intersecting, and they to introduce them, they are very if you don't know them, they are very nice homotopical invariant. For instance, they were known to be the complement of the links within the tree sphere is giving rise to very important questions in low-dimensional topology, which are for 3 dimensions. Those happened only in dimensions above 2. And for instance, I presented here how to construct usually breads and links and nodes using bread groups. So some kind of permutations. Some bread is a kind of permutation, and you can compose the permutation such that you obtain some either links or nodes. Depending on how you close them. So basically, the most simple figure is the Borromean knot, Borromean link. Where you have three rings which are linked by 3, but without any link by 2. So the function that I will use them are extremely classical in information theory. They are the joint entropy, which can be seen as a union in the Venn diagrams, but that can be seen also on the semi-lattice of joint random variables. So basically, here you have the first rank of the variables, the second the joint entropy of pair variable, triplets, and so on. And you have the conditional entropies are in one-to-one correspondence with the edge of the lattice. So basically, and you have the chain rules and so on. And basically, what is very so yeah, and you have the same with the mutual information and the with the intersections that you can represent also as the semi-lattice of intersections, and with the chain rule. And here I will particularly the mutual information is defined as an alternated sums of joint entropies, which is basically, for instance, the triple information is equal to the sum of the sum of the single variables minus the double variables plus the triplets variables, and the interaction information is just the twin functions, which which is just multiplying by -1 by alternating degrees, such that the even number of variables mutual informations are minus the interaction information are minus the interaction information. You have also the conditional mutual information and the chain rules for mutual information. Which, the other very important quantity for statistical is the total correlation, which is a Kullback-Leibler divergence, which is just the sums of the marginal entropies of single variable entropies minus the total joint entropies in this context. And there is a nice theorem of Euclidean that I illustrate here very informally, which state that which makes the analogy to set theory more rigorous. That state that there is a one-to-one correspondence with finite additive measurable functions with operators union, intersection, and complement with the corresponding joint, mutual, and conditional information operation respectively. So everything goes as in sets, just it is not the distributive, in fact. So one of the differences, it is not distributive. So what those functions represent, the interest for those functions is that their zero is in fact gives statistical independence, and you have the whole theorem that two variables are independent if and only if their mutual information is zero, and basically they are usually they correspond to some, in the pairwise case, to some generalization of the correlation of coefficient in statistics, and this can be extended to multivariate mutual information, in the sense that n variables are mutually independent if and only if all the mutual information in the semi-lattice I presented vanishes. And for the total correlation, in fact, it is sufficient that only the last one, the n variable total correlation vanishes. So basically, and there was also some theorem that characterized a Markov chain in terms of mutual information, of pairwise mutual information. So basically, what we see is that the usual form of statistical independence are characterized in terms of information theory, and that mutual information and interaction information give some refined statistical independence. So basically, here I remain the concavity of entropy, which basically here will be interpreted by the fact that the minima are on the boundaries of a simplex, of the area of the three simplex, three dimensional, the two simplex of probability with the entropy on it. And there was some previous work with Benquin. Unfortunately, the proof is not published, but it's which states that for the odd mutual information, odd the number of variables, the functions are super harmonic. So it's kind of weak concavity. So basically, it states that the minima will go on the boundaries. Are on the boundaries, and the opposite for even mutual information. So basically, in terms of interaction information, they will be all superharmonic, weakly concave. And basically, in the binary case, it's all. I forgot to say, it's all for binary variables. So in the binary case, we can up to some finite ambiguity, we can consider information quantities, as providing some coordinates on the probability law. Because so that's it. So now I will present the very basic case where synergy was found. So basically, for three binary variables, so you have three variables that can take two values, which typically was considered as spikes or no spike in the neural network settings. The function of triplet mutual information as four maxima, which is basically the usual maximally correlated configuration. So we are represented in terms of the space of the data. So basically, the variable are 0 or 1 in a three-dimensional space. And you see that the four minima achieved in the seven complex of probability, in the seven simplex of probability, are achieved for the correlated diagonals, where the correlation is maximum. But when we look at the minima of those functions, in fact, the minima is -1 bit. So basically, this is why it was quite surprising. You have negative information. And for those negative information, in fact, the variables are independent 2 by 2. So the mutual information, pairwise mutual information is 0. So whenever you project and it is achieved for 2 points in the simplex of probability, and whenever you project, in fact, on the two-dimensional subspace, on the two-dimensional, you have a full uncertainty, a fully uniform distribution. So basically, this appears purely only as the three-dimensional configurations, and we could show that those minima, in fact, there are two of those minima, which happens for 2 specific configurations where the probability simplex are either 0 or minus or 1/4 on the probability simplex. And we propose the analogy that it corresponds to kind of Borymerian 3 links, the right one and the left one. I forgot to say that Brownian links can be chiral, so you have the mirror image of the links that is also that can be distinguished. This phenomena also happens for ternary variables. In fact, we can find some configurations where the probability is 1/9 or 0, and all that is changed is that you change the basis of the logarithm in terms of information quantities, and then the basic idea was to look at if it could be generalized to those stuff to 4 variables. That would be the analog of 4 Brownian links, and this is in fact this can be done in fact. So basically, now you end up with a 15-dimensional simplex, and with interaction information of -1 bit, while all the lower order interaction information are 0, and so they are basically independent 2 by 2, 3 by 3, and so on. And this occurs, in fact, for 2 different configuration in the simplex, which is given by 1/8 or 0 configuration that were shown here. So it's which are in fact can be represented as in different configuration of the probability cube or the lattice of probability. So the 0 only connects the 0 values of the probability only connects 1/8 probabilities of the stuff. So the proof of this is very basic. So I use a combinatorics of independent equation system, and basically solving this equation system, I obtained the two values of the configurations. So this generalized to K-links using the previous remark that I made, and basically you have two configurations, the 2 configurations that represent the 2 Brownian links, the right one and the left one, for probability, which is 1/2 power k minus 1, and there is a nice interpretation of what's happening here in terms of general Kirkwood superposition approximation, which is basically due to I forgot their name. I should have pointed it, but there is a very nice publication that showed there is Matsuda first, who showed the interpretation of in terms of Kirkwood approximation. So the Kirkwood approximation is just is come from fluid mechanics and was derived in order to approximate statistical physics quantities. And the distribution law only by considering the K-first K-body interactions with K below n. So basically, we'll consider interactions of for strictly inferior up to the n variables. So basically, this is the Kirkwood approximation. And in fact, when you and here the example for 3 variables. And in fact, with this, we have exactly that the interaction information is the Kullback-Leibler divergence in between the probability and the Kirkwood approximation. And so, yes, and there is a very, just a remark which is quite informal, is that when in a more general settings, in measure settings, the K negativity, the Kullback divergence can be considered as possibly negative. And in this case, in fact, the Kullback, in this context, the Kullback divergence in between the Kirkwood approximation, the real probability distribution, and the Kirkwood approximation is negative whenever this is not a probability function. So basically, this does not. Whenever the Kullback-Leibler divergence becomes negative, it means that Q, the Kirkwood approximation, is not a probability function. It doesn't sum to 1. It goes below to 0. And then you can interpret the negativity as providing some inconsistent probability laws, which can be seen as a global inconsistent, okay. As a global consistent, but the local inconsistent decomposition. Okay, so in conclusion, so information links, so they are purely collective phenomena and phenomena interaction. Here we presented a very small subset of links, so it needs generalization and formalization. And yes, there was some nice, very general, more general result on contour information relating negativity of entropy functions to non-locality to Bell inequalities relations. So basically, and probably the right formalism will come also from Kovanov cohomology. Thank you.